In this video, I'm going to talk about using Python to control this little bit of circuit here, which is a real-time clock. So I put together this circuit board because I wanted to have little emblems next to the GPIO connectors from the Raspberry Pi. And I thought, well, rather than just make a little circuit board like that, why not add some extra circuit boards around it? So I've got an audio amplifier here, infrared transmitter and receiver here, and some transmitter and receivers for 315 megahertz and 433 megahertz, and the RF24L01 transmitter and receiver, which is a microwave transmitter and receiver. The real-time clock part of this circuit only requires 4 connections: 5 volt, 0 volt, and some I2C connectors, a serial clock and serial data. And the serial data is bidirectional, which is why you only need 2 wires to communicate with this. And although I'm connecting to the I2C part of the Raspberry Pi, in Python I'll just be simulating the I2C logic to actually drive and read and write to that real-time clock chip which is there. So this is how the application works. So I've just got the Python application, and if you just run it without any command line arguments, it tells you what options you have. So these are the operations you can do. So initialize, what that does is it takes the system time and it writes it to the real-time clock. I'll go through each of these as an example, and then you can set the system clock from the device time, from the real-time clock time, and you can read the system clock and the device date and time. Also a message, because it has a space to fit a little message in the device as well, which you can store, and you've got this option to actually set a message on the device. So if I first of all start off by doing the -G option to get what's currently on the device, and you can see the device time I've deliberately set to be the wrong date and time so that I can demonstrate initializing the device. And it's already got a test message in there, but if I use the -M option and in quotes type another message, and then I go -G again to get the options, and you see that the message has changed to another message, so you can set the message in there. The date and time is still incorrect, so it's set back at 2010, whereas it's 2020 now. So if I go -I, so this is what you do first of all, is you set your system time to be the correct time, then do -I, and that transfers the system time onto the real-time clock. So if I do a -G after that, now the system time and the real-time clock time and date are the same. So now you can switch off your Raspberry Pi, and you can turn on maybe a week later, and you've got the wrong date and time. So I'll simulate that by actually setting my system date to a different date. So this time I'll put 2011 01 11, and then midnight 30, something like that. So now if I go -G, I can see that the system time is what I've just set it to, but the real-time clock time is still the correct time. And if I do another -G, you see that real-time clock, so it's at 54 seconds there, now it's at 56:03. So the real-time clock is running in the background, and when you switch off the Raspberry Pi, it keeps running with the battery backup. So if I now go -S, that will set the system time from the real-time clock time. So if you do that, run this command boot up in the boot up script to set it as it boots up, and then if I go -G to get it again, and now the system time is the correct time because it's been taken from the real-time clock. So you just need to put this command in the boot script, and when Raspberry Pi boots up, it will automatically be the correct system time each time. So this is the circuit diagram I'm using. It's a very simple circuit. So the main integrated circuit is in the middle of the real-time clock. It's got a battery backup here, which goes between pin 3 and pin 4 ground. And there's a crystal connected directly on the side. You don't need any external capacitors for that crystal. Going between pin 1 and pin 2. And it's 32 kilohertz crystal, which divides down into exactly a second. And then there's power at the top, VCC, which is 5 volts, and an output. So you can set the output to be a clock pulse, which is what I've done. You can set it to other things as well. So I've set it to a 1 Hertz clock pulse, and all I do is drive a transistor, which lights a LED, flashes an LED every second. And then the only other 2 pins are the I2C communication pins, which go to the Raspberry Pi over here. And you don't need these resistors, but I like to put resistors in line with the GPIO pins on the Raspberry Pi just to be safe. And that's the circuit. So they're just 2 Python files which I'm using to do this demonstration. And the first one is the library which I'm going to use to do the I2C communication. At the very top, you set the GPIO pins you're going to use for the I2C communication. And they don't have to be the actual I2C Raspberry Pi communication pins, because it's simulating I2C communication, so you could actually use any pins you want. And there's a few little functions which I've taken out in order to make things read simpler in the actual main code. So the first function I've got is to initialize the GPIO pins to how they should be when there's no communication going on. So the initial for the data and the clock pins is to set them to high, and that indicates on the bus that the bus is idle and nothing's communicating on the bus. I've separated out a start communication indication. So because many devices can communicate on the bus, you have to tell all the devices on the bus when you're starting communication, when you're ending communication, so that they know when the bus is busy or not. So if you take the data line low and then you take the clock line low, all the devices then know, okay, you're about to use the bus and the bus is going to be busy. And at the end of communication, you take the clock line high and then the data line high, and then all the other devices on the bus know that the bus is now free, and if they wanted to, they could communicate. Well, I haven't written this library in a way that actually the other devices, any other devices, could communicate to each other. This is solely going to be this application which is using the communications. And also, when you write or read data, you have to acknowledge, or the device will acknowledge that the byte has been sent or read. So when you're writing, you have to read acknowledgements from the device, and it will tell you if it's received the data or not. And when you're reading, you have to write acknowledgements to the device to say that you've received the byte. But your acknowledgement's actually slightly different, because the very last byte you read, you actually send an acknowledgement of high, which says basically I'm not reading any more bytes. So the acknowledgements are really just to say, if I'm sending 0 or low level, it means I'm going to read another byte from you. But if you send a 1 or high level, then it's saying, okay, that's the last byte I'm going to read. I'm not going to read any more bytes from you. So then you come across the main routine, and the main routine does a start communication, and it goes through all the words that you want to send, or bytes, in this case the words bytes. So it goes through each of the bytes that you've passed in here that you want to send, and you've also told it how many bytes you want to read, and it will send out those bytes. Now you have to send out the address byte of a device that you want to talk to, so that's a mandatory thing that you need to send out first. And then it's up to you what other data bytes you need to send in order to communicate with the device, or how many bytes you want to read. So this top bit of the function just goes through each of the data bytes, and it goes through each of the bits in each of the data bytes and sends each bit out on the bus. So if it's a level 0, then it sets the data level to 0. If it's a 1 it wants to send, sets data level to 1, and then it takes the clock high and clock low to clock it into the device. So, and it just goes around that loop until it's written all the bits for each of the bytes that you want to send. After each byte, it will read the acknowledgement, because it needs to read that extra bit from the device as well. And then it goes into, if you want to read bytes, then it will go through, for every byte you want to read, it'll go around this loop. It sets the GPIO pin to input so that it can read the bits, and then it goes through each bit and reads them off of the data line. But first of all, it needs to set the clock high, because data is only valid on data line when the clock is high. it reads the bit, adds it to the byte that you're reading, and it takes clock low so that it's ready to read the next bit. And then at the end, because we're now reading bytes, we need to write an acknowledgement, and we write a 0, except for the very last byte that we want to read, in which case we acknowledge that with a high, so that the device knows we're not going to read any more bytes. And every byte that it reads, it appends it to this received data. It does an end communication to tell devices, okay, I've finished using the bus, and then it returns the received data if you wanted to receive any data back to the main application. That library does the bulk of the work, and it's so this is the main part of the application, which is, you saw me demonstrate actually on the display, going through all its operations. So I'll go through it quickly. So there's a number of different arguments that you can pass in. You pass in the switch, which is the -G for getting, or the -S for setting, or -I for initialization, or -M for setting the message. Only the message feature has an extra argument, which is the actual message itself. So that's identified as that argument. Then I have constants for the actual device, the real-time clock itself. So all of the different options that you can configure. I configure things like you can convert the number of the day number into like the actual text itself. I've done that here, and this is the configuration that I have by default, which sets up a 1 Hertz output square wave when you initialize. And then these are all the different addresses that you can, or the commands that you can do on the device. So the address itself is D0 when you want to write, or D1 when you want to read. So this is the first byte that goes out. And if you're writing a byte, then the first byte, the definition of the actual device documentation is you tell it what register you want to write to when you write in. So this is address 0, register 0, or you start writing at register 3 for writing the date, or you start writing a register 7 for writing the control character, or register 8 for writing the message. And if you keep writing extra bytes, and they go sequentially after that into the next register, so you can just put a string of bytes after that to write more characters into the additional registers. And if you want to read from a particular address, because you don't actually put the address here, so if I wanted to read the date, so this is for writing the date, but the reading the date doesn't have this extra register name, so you actually have to run the write command without any extra data, just these 2 bytes, and then that sets the register that you want to read from, so you can then issue a read command. So it's a little bit sort of complex like that, but nothing too complex. I've put a little function into display data, so when I'm writing like the ASCII message to display, because you can put characters which are non-ASCII in the message, I've just put a routine in here which displays ASCII characters, but if they're not ASCII characters, it displays the hex value of that data, just so it makes a bit more sense. Then I've just got like the info. If you don't provide an argument, it displays that on the screen. It sets up the GPIO pins to how required, and then it just goes through each of the different features. So this is the -I option, and it does whatever it needs to do for that. So I'm getting the current system time, and in there I set the data to be the current system time, and also setting the control byte. So this one here is where I set up the 1 Hertz output signal, because I'm setting the control byte to the data I want. And then I format the date that I've read at the top from the system into the data, and I'm just appending here. These are the extra. So for each one of these, I'm writing to the next register, writing to the next register. So I'm writing the month, day, the month, the year in sequence to each of the registers it needs to go into. Then I take that data and I just call the function which was in the library we discussed just a little while ago, and send all of that into the device as a command string. And that's the way that I do everything. So the time you construct your command that you want to send, and then you send the data. And so that's the initialization. So it sets the control character and the control register and the date and time. And then the M one is the setting the message. And all it does is take the extra command line argument, which is the argument for message, and it appends each of those characters to the data I'm going to send to the device, and it sends data in exactly the same way as you saw in the initialization. So the data is always being sent in that same fashion. But on this one, I then read back the data that I've written so that I can display on the screen the message that was written, just to verify it was written correctly. And this is where I display it on screen. Then there's the set option, which reads back the data from the real-time clock. So here we issue a read command, and then it formats a Linux command to set the date and time. So here's the command to set the date, and then it formats the data that's read back from the real-time clock, and then it reads the time, and it formats that on and appends it to the command. And then I do a system, a Linux system command to set the date on the system with what the date is that was read back from the real-time clock. And then finally the get command, and all I do is read each of the different types of registers. So the date or the time from the real-time clock, the date from the real-time clock, I display the message from the real-time clock, and then I display the system time and system date. I should say system date. I'm going to correct that now. And I display those on the display as well.